back into them.
You probably have heard that the universe started with the Big Bang almost 14 billion years ago, and from the Big Bang only hydrogen and helium were done. But all the other elements which are around us, potassium which is here in our bones, the air which we breathe, oxygen, carbon which is very important, all of these elements, they were done in stars in a later phase during the evolution of the universe, and it still happens today. Not our sun, but stars. Stars that are older. And for that, you need neutrons inside the star, because only if elements like iron capture neutrons, so fusion of a neutron with an iron nuclei, for example, that can lead in a series to the creation of heavier elements. Now is the question, where do the neutrons come from in the star? Because also they must be there in the core of the star. And that is exactly what we are studying. The reaction that produces these neutrons. And that is a fusion of a carbon nuclei and a helium nuclei, for example, or of a neon nuclei and a helium nuclei. We have to simulate the nuclear reactions, because if you just put them aside, that does not happen. You need a bit of energy, and we accelerate the helium nuclei, the alpha particles, and shoot them on what we call a target, which in that case would be either neon gas or carbon, particularly an isotope called carbon-13. Okay. Then, in our experiment, these nuclear reactions happen, and they emit neutrons, and we measure the neutrons with a detector surrounding our area where the nuclear reactions happened. Refurbished in Notre Dame recently. Major problems were your cables inside, which leads to high voltage sparks. Now that all has been replaced with fiber optics. So more plastic. And, Mark, could you help me? Basically the acceleration range. Here we will have what we call an ion source, which is basically just a reservoir of either hydrogen gas or helium gas, depending whether you want to accelerate protons or alpha particles. You can do one or the other, not both at the same time, but you have to replace the gas. You ionize the gas in a way that is necessary to get the nuclei out of this gas reservoir. Because only if they are ionized, that means one electron less, then you can accelerate them. This will be on ground, so you have the difference between 1 million volt and ground here, and that accelerates the particles and gives them a certain energy, and with that a certain velocity, which they exit the accelerator. It's the same place that Ray Davis 50 years ago made his groundbreaking discovery of solar neutrinos, which is connected to our research, because that was the proof that solar energy is provided by nuclear reactions, and here we are studying nuclear reactions. So everything is coming back in a circle. These kind of experiments are important to help us to understand where we are coming from, where the elements which surround us are generated, where they are created beyond the Big Bang.